Right. Hello everybody, this is Mr. Arocena, and on today's lesson we're going to continue our exploration of momentum, where we'll be talking about conservation of momentum. So if you remember from last lesson, we talked about momentum being the quantity of motion, and momentum being the product of mass times velocity. Okay? Now, conservation of momentum is actually kind of a byproduct of Newton's third law. So if you remember from our Newton's third law lesson, Newton's third law basically stated that if there was, for every force, there's an equal and opposite reaction force that happens. So like, remember if I mentioned if you excuse me, if you punch the wall punches back. Okay. Now, if we write the equation using the original form of Newton's second law, we can show that the force that some body A exerts on B is equal to this. This is, again, Newton's original second law was a change in momentum over change in time. And that has to equal the exact force that B exerts on A, just in the opposite direction. So this equation can be written for the force of B on A. And if you notice, these two values are the same, excuse me, the same, but in opposite directions. So the momentum that the momentum that changes on both objects is the same, they just happen to be in opposite directions. And this is true for all cases, especially if it's closed and ideal. Okay? So what this basically states is this is the conservation of momentum. And what that means is that the total momentum in a system does not change. So if you calculate the momentum before something happens and calculate the momentum after something happens, then both momentums will be the same. Now, usually what that thing is usually a collision of some sort. So P before this is like before a collision, usually. And then P after would be after a collision. Sometimes we deal with explosions. So when things explode, or things like that. I spelled explosion wrong. Let's change. Yeah, okay. Explosion. So that's usually what it means when we talk about things before and after. Explosion is that usually a collision will occur, two things will collide, or something will explode. That's usually how the problems are framed. Okay, we'll go through some more examples when I'm back, probably in our lab form or something like that. But the basic idea is that if you calculate the momentum before something happens, it's going to be equal to the momentum after it. Okay? Excuse me. We'll go through the first example here. All right, so a coal car of mass 6,000 kilograms is traveling with a velocity of 5.5 meters per second. When it hits another coal car of equal mass, what is the new velocity of the two coal cars if they stick together? So here's an example of two things sort of colliding with each other. So I'll draw a picture. You have a coal car kind of colliding with another coal car. This is our before case, before. And after, the two coal cars are stuck together, and they continue moving on this way. After. All right, let's grab. Go. All right. So both coal cars have a mass of 6,000 kilograms. So I can write that down. 6,000 kilograms. 6,000 kilograms. Excuse me. 6,000 kilograms. Okay, before, this one has a velocity of 0. This one has a velocity of 5.5 meters per second. And here, the combined mass has some unknown velocity. All right, so now I can calculate the momentum. So the momentums before, so P before, this will just basically be the sum of the momentums. So 6,000 kilograms times 5.5 meters per second plus 6,000 kilograms times 0 meters per second. This is, I don't actually have to do this particular calculation because this calculation just drops out to 0. I'm just showing that to make it explicit that you add the momentums of everything before they collide. Okay. All right, so calculating this, let's pull out my calculator. There we go. Slide over. So 6, let's make that smaller so you can see. Okay, there we go. Sorry about that. Not sure what my computer was doing. So 6,000 times 5.5, got 33,000. And momentum again has a strange unit of kilogram meters per second. Okay, that's the momentum before the collision. Now, what we know about this is that this momentum has to equal the momentum after the collision. So this has to equal the momentum after the collision. Okay, we're ignoring any losses of motion due to friction and whatnot. Okay, so in ideal system, this is what would happen. All right, so now we know what the momentum before is this value here, and this has to equal the momentum after. So we can set up the next equation as follows. 33,000 kilogram meters per second is the momentum after. Now, thankfully, in the after case, they stick together, so they have a combined mass of 12,000 kilograms, and they're traveling at some velocity, which we don't know, which we're trying to calculate, right? So now we can just do simple algebra. We'll divide this by 12,000 kilograms. Divide this by 12,000 kilograms. And we get the following. Where the velocity is equal to, let's see, this number divided by my mass. So total 2.75 meters per second. There we go. There. So that's how we can sort of use the conservation of momentum to help us solve a problem like this, because we know that whatever the momentum is before has to equal the momentum after. And then we can usually calculate one of the two and then just sort of use this sort of bridging to show that if I know one of those momentums, I can set it equal to the other and then analyze the situation to show that. Okay. And again, your momentums before will just equal whatever the momentums are of object 1 plus object 2, and then if you have third object, you can put whatever and so on. And then the momentum after can be calculated the same way. Momentum of your first object plus your second object plus your third object plus so on. And this is important to remember because sometimes the objects don't stick together. So quite often what you'll find is that if one object hits another object like this before, the after case, they might end up traveling separately, just a little bit slower. You'll see this if you ever go to Mr. Hara's room and play pool in his room. You will see sometimes when you play pool that if you hit one of the pool balls, one pool ball will sort of trail behind the other, depending on how they're hit. Okay. And they don't always fully transfer the momentum. Other times, like again, other times if you get a pool ball hitting another pool ball, the first one will stand still and the other one will just move with basically all the momentum of the first ball. Okay. So there are lots of situations where you can sort of see this. Okay. There's one more example. Hopefully I don't, my voice holds out. Okay, so here we'll take a similar example to what I mentioned last week. We didn't actually calculate this, but we did talk about it a little bit. Okay, there you go. So here we have our bullet being fired from a rifle with a velocity of 600 meters per second. Okay. I forget where I took this data from. I think it's either a standard hunting rifle. I don't think it's a sniper rifle. I think actually some of the most powerful sniper rifles in the world can reach velocities of close to a kilometer per second, I think. Anyways, what is the recoil velocity of this particular rifle? Okay, so the recoil velocity is basically the velocity of the rifle if it was not being held down. Okay, so if I were to draw this, okay, so let's draw the rifle. Here's my rifle, and then the bullet is getting shot out of the rifle this way. The rifle will recoil backwards this way with some velocity. So here the bullet has a velocity of 600 meters per second with a mass of 0.06 kilograms, and the rifle has some velocity and the mass is 3 kilograms. Okay. Now this is actually the after case. So I'm going to slide it down here. Okay, so this is actually the after case. What's the before case look like? Well, the before case is pretty much the same, just everything is stationary. So I'll just copy this. Whoops, I want to paste it now. Edit, paste. So this is the before case. Everything is kind of stationary before the bullet leaves, before the bullet gets, so this is the before. So before, everything is stationary. Okay, so before the bullet gets fired, before the bullet cartridge explodes and shoots the bullet outwards, everything has a velocity of 0. Now this is great because now we can show that the momentum before is really easy to calculate. Because nothing is moving, the momentum before has to be 0 kilogram meters per second, which is awesome because now when we calculate the momentum after the bullet explodes, because we know that the momentum before, these two have to be equal, then the momentum after has to also equal 0 kilogram meters per second. Now some of you might be wondering, well, how's that possible? Because in the after case, the bullet is moving this direction, the rifle's moving that direction, so they have some momentum. But don't forget, in order to calculate the after momentum, you have to take into account the momentum of all the objects in motion. In this case, we have two objects in motion, the bullet and then the rifle. So, and the other thing to notice is that they're moving in opposite directions. So when we calculate this, our first object, we'll take that as the bullet. So 0.06 kilograms times, whoops, not 300, 600 meters per second. Then we're going to add this to our momentum of our rifle with a velocity of some amount. And all this has to equal 0. Okay. Now the answer you get will end up being negative, and it'll make sense. It'll make sense. So when I calculate this out, let's see, 0.06 times 600. This is 36 kilogram meters per second, plus 3.0 kilograms times V. We'll call that V2. Should have labeled these ones so they're separate. Okay, bringing this over, we'll subtract 36, so negative 36 kilogram meters per second equals 3.0 kilograms times V, okay, or V2, and then we'll divide by 3, and we get negative 12 meters per second equals V2. Alright, somebody wondering is why is this negative? Well, the only reason this is negative is because of how I've drawn my picture. Because I had my positive 600 meters per second going in this direction, so anything going in the other direction has to be negative. Okay. So that's why it's a negative answer. It just means, so that negative answer means it's going in the opposite direction. So this negative means opposite direction. Okay. So if you get a negative velocity, it means that whatever that object is moving in the opposite direction of the other object. Okay. And this matches up perfectly well with what we've experienced. If you think back to the physics cart lab we did last week, where we had our two physics carts, like so. And then we had one cart push on this cart. Well, according to Newton's third law, the other cart has to push this way, and then both carts kind of move in opposite directions, like that, right? So one cart would be having a positive velocity, the other cart have a negative velocity. The negative velocity, again, is only because the cart is moving in the opposite direction. Okay. And we'll talk about this actually in a lot more detail in the next unit, what direction actually means. For now, the negative just basically means just the opposite direction of the other object. Okay. And it should make sense because if, according to Newton's third law, and if any of you guys have fired a rifle, you will know that the rifle does recoil backwards. Some of you might be wondering, why does the rifle recoil so violently? Why is it so large? Why is it this? Well, keep in mind that in the example, no one's holding the rifle, so it's just the rifle. If somebody were holding the rifle, so let's say somebody were holding the rifle. So let's grab this equation here. Okay. So if somebody were holding the rifle, the amount of recoil velocity would actually be quite a bit smaller. So if somebody, even say like a 53 kilogram person were holding the rifle, then you do the same math, and then this would be the recoil velocity of that person, right? So if somebody were holding the rifle, then we get 36 divided by 3, so 0.68 meters. Right, there you go. So as you add more mass to one side, the momentum is still conserved, but the added mass helps explain why some things don't recoil as much as you would expect them to recoil. Like here, if somebody had a mass of 50 kilograms and they were holding this rifle, they'd only recoil with a velocity of 0.68 meters per second, which is still quite a bit, because that's like over half a meter per second. So if you're not expecting it, you'll probably get blown back about half a meter or so. Mind you, if nobody is holding the rifle, you're being blown back, or the rifle's being shot back at negative 12 meters per second. And that's quite a bit more. That's, yeah, that's quite a bit. Okay. Anyways, To reiterate, and go back, it's gone now, but to reiterate, conservation of momentum, whatever momentum you have before something happens has to equal the momentum after it happens. Okay. And this is true for any closed system. Closed systems are basically anything that doesn't lose energy, which is actually kind of an impossibility in most cases. But for the most part, if we can reduce friction amounts, this is true. Okay. All right. Your assignment for today then is as follows. Okay. There you go. And we'll see you guys next time.